To understand the concept of entropy, it's a good idea to solve number of numericals so that the concepts get internalized. So the plan is to derive some expressions for entropy change of ideal gases, which can be used to solve numericals dealing with the systems involving ideal gases. Now, in the real life, you won't find applications where ideal gases are used as a working fluid. However, one can approximate the systems which uses gases in substantial proportions as the systems with ideal gases. For example, internal combustion engines, we can model it as those engines which operate on ideal gases and do the analysis, which gives us useful results. What we would be discussing right now, some numericals on the entropy change of gases. So let me go to the place where I had derived some interesting expression for ideal gases. So let us go to the new screen wherein I would be showing you the expression for ideal gases. Please bear with me. Yeah, and now here you would find, yes. So what you would find here is, I have some very interesting expressions for entropy change of ideal gases. I have considered closed systems as well as open systems for deriving the expression for entropy change of gases. So the first case I am considering, as you see on the screen, is the entropy change of gases when we are dealing with the closed system. Closed system means there is no mass transfer. When there is a closed system, the work transfer can be obtained by from the pressure volume diagram, and it is the area under the pressure volume diagram. Mathematically speaking, the work transfer is given by integration of PdV, pressure into change in volume. If it is an open system, the work transfer is obtained by the area behind the pressure volume diagram, the area behind the process drawn on a pressure volume diagram, and mathematically it is W is equal to minus integral of VdP. Okay, so these things we need to keep in mind. We also know that the first law of thermodynamics, as applied to a process, when you are talking about a closed system, is given as Q is equal to delta U plus W, where Q is the heat transfer, delta U is the change in internal energy, and W is the work transfer in the closed system. So when I consider the first case where you see on the screen, I have written a closed system constant volume process. So I'm talking about a constant volume process. So in a real life, if you consider any system whose volume is constant, then how do you calculate the entropy change if the working fluid is a gas? So for that, we can consider a piston cylinder arrangement wherein the volume is constant. Volume is not changing, so it's a rigid piston cylinder arrangement where the volume is constant. In such a case, W is equal to integral of PdV. So the piston is not moving, piston is not allowed to move. It's a constant volume process, so the work done is equal to integral of PdV is equal to 0 because change in volume is equal to 0. So when W is 0, because dV is 0, so Q becomes equals to delta U because W is 0. That is, the heat transfer is equal to the change in internal energy. So Q is equal to delta U, and from the definition of delta U, you know that change in internal energy is mCV dt. So there is a correction over here. Here it has to be mCV, not delta U, mCV delta T. Okay, so mass into specific volume, mass into specific heat into change in temperature. In a differential form, you can say del Q is equal to mCv dt, where m is the mass, Cv is the specific heat at constant volume, and dt is the differential change in temperature. Because from the definition of entropy change, we know that entropy change is dq upon T. So this expression becomes ds is equal to dq is mCv dt upon T. And as we have studied in calculus mathematics, delta S we can obtain by integrating ds. And if we integrate this ds for a process from 1 to 2, it becomes integration of mCv dt by T, which gives us a very useful expression for determination of entropy change for a closed system undergoing a constant volume process, which is mCv log to the base e T2 upon T1. So the change in entropy when the system is a closed system and the process is a constant volume process can be calculated by the expression delta S is equal to mCv, that is a specific heat at constant volume, into ln, which is log to the base e of T2 by T1, where T2 is the final temperature and T1 is the initial temperature. Similarly, if the system is an open system, and again when we talk about open system, in our course we will be dealing only with the steady flow system. So for a steady flow system, as was discussed, the work transfer is given by the area behind the pressure volume diagram, which is minus integral of VdP work. And because the V is constant, specific volume is constant, we can take as outside the integral, and then that becomes minus V into P2 minus P1. Using the gas equation PV is equal to mRT, and this expression can be written as, because PV is equal to mRT, so this expression is minus mR into T2 minus T1. Okay, so this expression gives us the work transfer. But we are interested in not only the work transfer, but also the entropy change during the steady flow system, constant volume process, constant specific volume process. So for that, we need to calculate dq and divide it by T. Now dq is dh plus the dw, and that gives us dh minus vdp, which is du, from the definition of enthalpy, because enthalpy is u plus pv. So dh is equal to, so dh minus vdp is equal to du. Okay, so this gives us q is equal to du, and you can put this dq as du in the expression of ds. So for calculating the entropy change, which is equal to du upon t, gives us mCv dt upon t, and the similar expression which was for the closed system, we also get it from the open system, wherein the change in entropy from integration is mCv ln T2 by T1. So for an open system, and I'm talking about a special case of open system, namely the steady flow energy equation, steady flow open system, undergoing a constant volume process 1 to 2, the entropy change can be calculated as mCv ln T2 by T1. Similarly, we can get some such expressions for entropy change of gases for other processes like constant pressure process, constant temperature process, or let us say adiabatic process, hyperbolic process, polytropic process, and so on. Okay, so let us discuss those processes and the respective derivations in the next class. Thank you very much.